Welcome back to the Deep Dive.
Great to be here.
Today, we are taking you far, far above the clouds. Think volcanic peaks, Canary Islands.
Ah, La Palma.
Exactly, where an absolute engineering giant stands guard over the universe. We're talking about the Gran Telescopio Canarias, the GTC.
It really is something else. More than just, a telescope. It's this incredible monument to collaboration, to cutting-edge engineering.
And that's our mission for this deep dive, isn't it? To really unpack this titan. We want to focus on the sheer scale, the tech, the instruments, and just the unbelievable effort it took to even build it there.
Yeah, the logistics alone are mind-boggling.
So let's jump right in with the scale. Context is everything here. When we say GTC, we're talking about the world's largest single-aperture optical telescope.
That title really matters. Single aperture. It's not an array. It's one giant eye on the sky. And that comes with, well, massive complexity.
The numbers themselves are just staggering. What are we looking at for the primary mirror?
Okay, so the diameter is 10.4 meters. That's 410 inches across.
410 inches? Hard to even picture.
And that translates to a collecting area of 78.54 square meters.
78 square meters, just pause on that. That's like a decent-sized apartment. Maybe a small house?
Pretty much, yeah. But instead of walls and furniture, it's this perfectly formed surface designed for one thing,
right.
Grabbing photons.
The faintest, oldest light that's traveled, billions of years across the cosmos.
Exactly. And you need that immense light-gathering power because of where it is, or rather, the location enables the science that needs that power.
Right. The Roque de los Muchachos Observatory, La Palma, Canary Islands, Spain.
One of the best observing sites in the Northern Hemisphere. Dark skies, stable atmosphere.
Mostly.
Oh, the catch. It's high up, right? Very high. We're talking 2,267 meters. That's over 7,400 feet above sea level.
Okay, so stunning views, clear air, but getting stuff up there.
That's the Herculean task. Imagine hauling multi-ton, incredibly delicate pieces of equipment up a remote mountain road on an island in the middle of the Atlantic.
Yeah, the logistics sound nightmarish.
It really was a battle against geography from day one. The sources are clear, construction was tough, they faced constant challenges with weather, just unpredictable high-altitude maritime conditions.
Wind, storms, maybe clouds rolling in unexpectedly.
All of that. Plus just the sheer difficulty of transport and assembly in such a remote spot. It took decades of planning before they even broke ground, just to figure out if it was even feasible.
So this wasn't a quick project. It speaks to that long-term vision you need for fundamental science. When did the idea first spark?
The planning phase kicked off way back in 1987.
87. So people were envisioning this specific telescope over 2 decades before it saw, first light.
That's right. It shows incredible commitment, doesn't it? Thinking that far ahead, securing funding, coordinating internationally, it's rare.
And from 87 planning to actual operation, that's a long road.
How long did the physical construction take once it got going?
Once they really started building, it was 7 intense years.
7 years on a mountaintop. And the cost must have been astronomical itself. The final figure was staggering, yeah. Around $130 million.
Wow. And that money represents what? Materials, yes, but also the human effort.
Oh, massively. The sources say over 1,000 people were involved from maybe 100 different companies.
1,000 people, 100 companies, all focused on this one project, coordinating that.
Across different countries, different specialties, engineers, manufacturers, construction crews, all working on a remote site for 7 years.
Mm-hmm.
Honestly, sometimes the organizational challenge seems as big as the technical one.
Okay, let's walk through the milestones. When did it actually start seeing the sky? The famous first light.
That happened on July 13th, 2007. A huge moment, obviously. Proof that the core systems worked.
But that wasn't the full telescope yet, was it?
No, not at all. That 2007 first light was a test run. They were only using 12 of the final 36 primary mirror segments then.
Ah, okay. So it was a crucial test, especially for the mirror control system.
Exactly. To prove they could control even a fraction of the mirror with the required precision. The full scientific operations, using more segments and the first calibrated instruments, didn't officially start until May 2009.
And then the big celebration.
July 24, 2009, the formal inauguration. King Juan Carlos III of Spain was there, over 500 people. A real marker that this world-class facility was fully open for business, celebrating the technology, the ambition, everything.
Incredible story just getting it built. Now let's dive into that centerpiece, The 10.4-meter mirror, you can't just make a single piece of glass that big, right? It would deform under its own weight.
Exactly. Physics puts a hard limit on monolithic mirrors. Transporting it, polishing it perfectly, keeping it from sagging or warping due to temperature changes. It's just not feasible at that scale.
So how did GTC solve that fundamental problem?
Modularity. It's a segmented mirror design. Instead of one giant slab, the primary mirror is this incredibly precise mosaic.
Made up of
36 individual hexagonal segments.
hexagons. Why that shape? Is it just about fitting them together neatly?
That's a big part of it, yeah. Hexagons tile a roughly circular area very efficiently, minimizing the gaps between segments and maximizing the light collection. But the material they're made from is just as crucial.
Right, you mentioned the material science. What are these hexagons made of?
They're made from a special glass ceramic called Zeradur. It's manufactured by the German company Schott AG.
Zeradur. What's special about it? Why not just, really good glass?
Because Zeradur has an extremely low coefficient of thermal expansion. Basically, it barely expands when heated or contracts when cooled.
Ah, so it's incredibly stable regardless of temperature shifts.
Precisely. Think about the temperature swings up there at 7,400 feet, night to day, season to season. Regular glass would distort, ruining the image quality. Zeradur stays put, absolutely vital for optical perfection.
Okay, so we have 36 super stable individual hexagonal mirrors, but how do you make them act like one perfect single mirror surface? Just putting them next to each other isn't enough, surely. Gravity, wind, they'd constantly shift slightly.
They absolutely would. And that's where the real magic, the critical engineering challenge comes in. The active optics control system.
The brain of the telescope.
You could call it that. It's constantly monitoring the alignment. It uses sensors typically analyzing the wavefront, the shape of the incoming light waves, to detect minuscule errors in how the segments are positioned relative to each other, even tiny misalignments.
And when it detects an error, how does it physically fix it? Push the segments around?
Essentially, yes. Beneath each of the 36 segments, there are hundreds of precision actuators. Think of them as tiny, incredibly precise electromechanical pistons.
Hundreds of them. Wow.
Yeah. And they receive constant commands from the control system based on the sensor readings. They continuously push and pull on the back of each segment, making tiny adjustments.
How tiny are we talking?
We're talking adjustments down to the nanometer level.
Nanometers. That's billionths of a meter.
Yeah.
And it's doing this constantly, in real time.
Constantly. Dozens of times every second. It's fighting gravity as the telescope tracks across the sky, counteracting wind pressure, compensating for tiny thermal changes in the support structure.
It's actively reshaping the mirror surface second by second.
That's exactly what it's doing. It ensures all 36 segments maintain that perfect, unified hyperbolic shape needed to bring light to a sharp focus. Without that active system, the incredibly long focal length, 169.9 meters, would be impossible to maintain with any clarity.
170 meters focal length, held stable by nanometer adjustments.
It's an astonishing feat of engineering. And honestly, the success of active optics at this scale on the GTC really paved the way. It proved the concept for the even larger segmented telescopes being designed now.
Right, the extremely large telescopes. We'll come back to that. But this engineering marvel needed funding, international buy-in. You mentioned collaboration earlier. How is the GTC project structured?
It's a formal partnership. This is pretty common for big astronomy projects today, sharing the cost and the observing time.
Who are the main players in this partnership?
It's primarily led by Spanish institutions, particularly the Instituto de Astrofísica de Canarias, the IAC, but crucially, it includes partners from North America too.
Which ones?
Specifically, institutions from Mexico, the National Autonomous University of Mexico, UNAM, and from the U.S., the University of Florida.
So it's not just a loose agreement, it's a structured deal tying funding to access.
Exactly. It's very pragmatic. The amount of funding each partner contributes directly determines their share of the observing time on the telescope.
How does that break down for the GTC?
Spain, providing the lion's share of the funding, gets 90% of the telescope time. Then Mexico and the University of Florida each contributed funding that translates to 5% of the observing time.
That makes sense. It spreads the financial burden and guarantees access for researchers from all of the contributing partners. Ensures stability too, presumably.
It does. Everyone has a stake in its success. Researchers from Spain, Mexico, and Florida all get guaranteed time on the world's biggest optical telescope. It's a win-win model, really.
Okay, so we have the colossal structure, the incredible mirror tech, the international backing. Now let's turn to what actually does the science, the instruments. The telescope is the light bucket, but the instruments analyze that light, right?
Precisely. The instruments are the scientific engines. They're what make the GTC so versatile. It's not just looking at one type of light. It has tools for observing across a huge range of the electromagnetic spectrum.
Visible light, obviously, but
Also near infrared and even into the thermal infrared, which is notoriously tricky to work with.
Let's start with one of the first instruments, a real workhorse, OSIRIS. What does that stand for?
OSIRIS is the optical system for imaging and low-resolution integrated spectroscopy.
Okay, so imaging and spectroscopy. In what wavelengths does it operate?
It covers the familiar visible light spectrum, but also pushes into the near-infrared. Specifically, the range is about 0.365 to 1.05 micrometers.
And why is that range useful?
Well, it's great for studying everything from stars in our own galaxy to relatively distant galaxies. A lot of key diagnostic spectral lines fall in that range.
And you said imaging and spectroscopy. It does both.
Yes, it's got a dual mode, which is really efficient. It can act as a high-quality camera, taking pictures over a pretty decent area of the sky, a 7x7 arc-minute field of view.
Which is how big, roughly?
About a fifth the width of the full moon, something like that. And then it can switch to being a low-resolution spectrograph, covering a slightly different field, 8 by 5.2 arc minutes.
So astronomers can find something interesting in an image and immediately get a basic spectrum to see what it's made of.
Exactly. Saves valuable telescope time. You don't have to switch instruments. And one neat feature of OSIRIS is its use of tunable filters.
Tunable filters. What do they do?
Instead of just standard broadband filters like red, green, blue, tunable filters, allow astronomers to select a very, very narrow slice of wavelength, like pinpointing the specific light emitted by hydrogen gas at a particular redshift, or maybe oxygen.
So you can filter out almost all the background noise and just see the light you're interested in.
Precisely. It makes it incredibly efficient for finding faint objects with specific chemical signatures, especially in surveys.
Very clever. Okay, beyond OSIRIS, there are other, more specialized tools. Tell us briefly about EMIR and HyperCam.
Right, EMIR is the Espectrografo Multi-Objeto Infrarrojo. As the name suggests, it's focused on the near-infrared, and it's a multi-object spectrograph.
Infrared. So that's key for looking through dust.
Absolutely critical.
Yeah.
If you want to see into the dusty center of our galaxy or look at stars forming inside dense molecular clouds, visible light gets blocked. Infrared light punches right through. That's EMIR's domain.
And also for looking at very distant objects because of redshift.
Exactly. The expansion of the universe stretches the light from the most distant galaxies, shifting it towards redder, longer wavelengths into the infrared. So EMIR lets us peer back deeper into cosmic time.
And HyperCam. Sounds fast.
It is. HyperCam is a high-speed optical camera. It's designed to capture things that happen incredibly quickly, transient phenomena, changing on timescales of milliseconds.
Milliseconds. What kind of events are we talking about?
Things like stellar occultations when an asteroid briefly blocks a star's light, or the rapid flickering you see from pulsars. Some types of supernovae have very fast changes in brightness early on. HyperCam needs incredibly fast readout electronics to essentially get freeze frames of these super fast cosmic events.
Wow. Okay, so we have versatile workhorses and specialized sprinters. Now let's get into the really complex cutting-edge instruments, Megra and CanariCam.
Yeah, these two really showcase the level of precision engineering and data handling that GTC enables. They push the boundaries.
Let's start with Megra. Multi-Spectrografo in GTC, the Alta Resolución para Astronomía. The key phrase there is high resolution. What does that mean in practice, and why is it important?
High-resolution spectroscopy is about dissecting light into its component colors, its wavelengths, with extreme detail. Megra operates at a spectral resolution, denoted by R, between 6,000 and 20,000.
R equals 20,000. What does that number actually tell us? How fine a detail can it see?
R is basically the wavelength divided by the smallest difference in wavelength you can distinguish.
Right.
So at R 20,000, you can separate spectral features that are only 1/20,000th of the wavelength apart.
Okay, still a bit abstract. Give me an analogy. What can an astronomer do with that kind of resolution that they couldn't do with, say, OSIRIS's low resolution?
Okay, think of it like this. Low resolution tells you if a car is moving towards you or away from you. High resolution tells you the exact speed, maybe even lets you hear the engine's specific hum.
Ah, okay. So for stars and galaxies.
With R20,000, you can measure the subtle Doppler shifts caused by turbulence inside a gas cloud. You can distinguish between different isotopes of the same element. You can precisely measure the rotation speed of a distant star by seeing the slight difference in speed between the edge moving towards us and the edge moving away.
So it unlocks really fine-grained physics,
I agree.
chemical composition, temperature, internal speeds, pressures.
Exactly. All across its wavelength range, which covers visible light and the near-infrared, similar to OSIRIS, but with vastly more detail.
But MEGR isn't just about resolution. It's about how it gathers that high-res data, right? It has different modes. Let's talk about the IFU mode first.
Right, the integral field unit mode. Specifically, MEGR uses something called the Large Compact Bundle, or LCB IFU. This is really cool tech.
How does it work?
Instead of getting a single spectrum from one point, the IFU takes a spectrum simultaneously for every single point within a small patch of sky. For the LCB, that patch is 12.5 by 11.3 arcseconds.
So you get a 2D map, but at every pixel on the map, you also have a full high-resolution spectrum, like a data cube.
Exactly. 2 spatial dimensions, 1 spectral dimension. You don't just know what elements are in a galaxy, you know where they are within that galaxy. Incredibly powerful for understanding structure and dynamics.
That sounds amazing. But then there's the other mode, the MOS mode, multi-object spectroscopy.
Yes, and if the IFU is powerful, the MOS mode is all about efficiency for large surveys. It's breathtaking, really. MEGR's MOS mode can observe up to 92 different objects at the same time.
92, simultaneously. Within what area?
Within a much larger field of view, 3.5 by 3.5 arc minutes.
Hold on. 92 separate targets scattered across that field. How on earth do you point 92 individual detectors, or whatever they are, at those specific pinpricks of light? That sounds like robotic chaos.
It's an engineering marvel. This is the aha moment. The system relies on optical fibers, thousands of them.
Optical fibers, like for internet?
Sort of, but much more specialized. There are 12,267 individual fibers, each with a core diameter of just 100 micrometers.
100 micrometers. That's about the thickness of a human hair.
Pretty much, yeah. These fibers run from the telescope's focal plane where the image forms, down to the spectrograph instrument itself, which sits off to the side.
Okay, so fibers carry the light. But how do you get the light from just those 92 specific target stars or galaxies into their designated fibers?
So that's where the robots come in. In the MOS mode, they use 92 individual robotic positioners, tiny little robots. Each one holds the input end of a small bundle of those optical fibers, along with a tiny lens called a microlens.
92 little robots buzzing around the focal plane.
Essentially, yes. Before an observation, the system calculates where each target will fall on the focal plane. Then these 92 robotic positioners move across the plane with micron-level accuracy, each positioning its fiber bundle precisely onto its assigned star or galaxy.
That is incredible. The precision needed for 92 robots to independently place 100-micron fiber ends repeatedly, accurately, on a mountaintop.
In a structure that's tilting, subject to vibrations, temperature changes.
Yeah. It's arguably one of the most complex pieces of precision engineering on the entire telescope, a true testament to what's possible.
Absolutely stunning. Okay, let's shift gears from visible and near-infrared light, captured by fibers, to something different.
Heat.
Thermal infrared. That brings us to Canaricam.
Right. Canaricam was a specialized instrument designed specifically for the thermal infrared range, roughly 7.5 to 25 micrometers. And it was optimized as a diffraction-limited imager, meaning it aimed for the sharpest possible images allowed by the telescope size at those wavelengths. Thermal infrared. That's where things get really challenging with background noise, isn't it? Because the telescope itself glows with heat.
Exactly. Everything around us, unless it's near absolute zero, emits infrared radiation. The telescope structure, the dome, even the instrument itself. They all produce a thermal background glow that can easily swamp the incredibly faint heat signals coming from distant astronomical objects.
So the solution is to make the instrument incredibly cold.
Extremely cold. You have to cool the detector and the optics down to temperatures where their own thermal emission is negligible.
And traditionally, for these mid-infrared wavelengths, that meant using liquid cryogens, right? Like liquid helium.
Yes, liquid helium gets you down to about 4 Kelvin, which is extremely cold. But it's expensive, it boils off, you need constant refills. And imagine the logistics of getting regular deliveries of liquid helium up to the Roque Los Muchachos Observatory.
Yeah, 7,400 feet up a volcano on an island. Sounds like a nightmare.
It would have been. And that leads to one of the key engineering innovations of Canaricam. It was explicitly designed not to use liquid helium.
Really, that was a requirement. How did they get around it? How did they achieve the necessary cold temperatures?
They developed a sophisticated closed-cycle cryocooler system. Think of it like a very, very advanced refrigerator. But instead of cooling your food to a few degrees above freezing, it's going down to near absolute zero.
Closed cycle, meaning it reuses its coolant, it doesn't vent anything.
Exactly. It uses mechanical compressors and expanders in multiple stages to reach extremely low temperatures without consuming any liquid cryogens. Much more sustainable and operationally simpler for a remote site.
How cold did this system actually get the instrument?
It was a two-stage system. The main optics and the internal structure of the cryostat were cooled down to about 28 Kelvin. That's minus 245 Celsius.
Minus 245 C, already incredibly cold. But the detector needed to be even colder, I assume.
Oh, yes. To minimize its own thermal noise and achieve peak sensitivity, the detector itself was cooled even further, down to approximately 8 Kelvin.
8 Kelvin. That's only 8 degrees above absolute zero, minus 265 Celsius.
For perspective, the cosmic microwave background radiation, the leftover heat from the Big Bang, is about 3 Kelvin. So CanariCamp's detector was operating just a few degrees warmer than the coldest thing in the universe, using only this self-contained mechanical cooling system.
That's phenomenal engineering, and they had to fit all this complex cooling tech into a reasonably sized package.
Yes, there were physical constraints too. The total weight of the cryostat, the cooled enclosure, and all its associated electronics had to be kept under 400 kilograms.
So CanariCam really proves something important about sustainable cooling for these challenging wavelengths.
Absolutely. It showed that closed-cycle coolers could meet the extreme demands of mid-infrared astronomy, paving the way for future instruments without reliance on liquid helium. Even though CanariCam itself was decommissioned in February 2021, as technology moves on, the lessons learned from its cryogenic system were invaluable.
Okay, let's pull back and summarize. What are the key takeaways for someone learning about the Gran Telescopio Canarias?
Well, first, just the sheer scale. That 10.4-meter primary mirror, the 78 square meters collecting photons, it's immense.
Second, the absolute necessity and brilliance of the segmented mirror technology, making 36 separate pieces act as one perfect, actively controlled surface. That's the core enabling tech.
Definitely. And third, you can't forget the power of international collaboration. Spain, Mexico, the University of Florida, pooling resources, funding, and expertise over decades to make something this ambitious happen. That partnership model is crucial.
And we saw how this incredible platform supports a suite of powerful instruments, from the versatile OSIRIS to the high-precision Megara with its 92 little robots.
To the innovative cooling of CanariCam. It really covers a lot of scientific ground.
And it solidifies La Palma's place, doesn't it? Roque de los Muchachos stands right alongside those other legendary observatory sites, La Silla in Chile, Mauna Kea in Hawaii, Paranal, also in Chile. GTC keeps it world-class.
Absolutely. It's still the largest single-aperture optical telescope operating today, pushing boundaries.
Which leads us nicely to a final thought, something for you, the listener, to mull over.
Yeah, think about that segmented mirror technology again. The GTC proving that 36 actively controlled segments could work perfectly at the 10-meter scale. That wasn't just for the GTC itself, was it?
No, it was the essential proof of concept, the technological stepping stone, wasn't it?
Exactly. The success of the GTC and other segmented telescopes like Keck directly enabled the next generation, the extremely large telescopes currently under construction. We're talking 30-meter, even nearly 40-meter class telescopes.
Which are entirely reliant on segmented mirrors, hundreds or even thousands of them.
Completely. They simply couldn't exist without the complex, modular, active control techniques that were pioneered and perfected on instruments like the GTC. It showed the path forward.
And one more thought, building on CanariCam.
Right, the cooling technology. What does it really mean for the future? The proven ability to get instruments down to 8 Kelvin using self-contained closed-cycle systems without needing liquid helium.
It makes things cheaper, more sustainable, maybe enables observatories in even more remote places.
That's the implication, isn't it? Lower operational costs, less logistical complexity. It could make putting highly sensitive infrared instruments in incredibly isolated locations, maybe even space, maybe the moon someday, much more feasible. The engineering solutions developed on a volcanic island in the Atlantic could well be charting the future course of deep space observation.
A fascinating thought to end on. The ripples from projects like the GTC extend far beyond just the science they produce today.
Indeed they do. Thanks for joining us on this deep dive into the Gran Telescopio Canarias.
We'll catch you next time for another look inside the sources. Welcome to the deep dive. We're here, as always, to really cut through the noise and get you the core, fascinating facts. Today, we are exploring something really deep-seated, I think. It's this almost universal human obsession, finding hidden, maybe mystical meaning in just, well, in numbers, counting. We're diving deep into numerology, this belief that numbers have some kind of occult or maybe divine link to events, and also that ancient practice of giving number values to letters and words and names.
Exactly, and we're going to trace this idea right from, its earliest documented uses, literally carved onto city walls, through some pretty esoteric studies in the Renaissance, and then right up to today, where it plays this, well, frankly, polarizing role in pop culture and maybe even surprisingly in theoretical physics.
Right, so the big question we're tackling is why? Why are humans seemingly so compelled across cultures and time to find these ordered meanings in numerical patterns?
It's a fundamental question, really.
And just before we properly jump in, here's a little linguistic fact for you, something I found quite surprising. The word numerology itself, it's actually pretty modern. It doesn't really show up in English until around 1907.
Oh, really? That late?
Yeah. For thousands of years before that, this whole practice was known by a different name, arithmancy, which is just a fantastic Greek term, right? It combines arithmos for number and mantia for divination.
Arithmancy. I like that. It's much more direct, isn't it? Number divination.
Definitely. Okay, so diving into the history, where does this all begin?
Well, the first thing that jumps out from the sources is just how incredibly ancient this is. Seriously ancient. Number symbolism wasn't some, niche hobby for mystics. It was deeply woven into the fabric of early civilizations, their philosophy, their religion, how they understood reality itself.
So numbers weren't just for counting sheep or taxes.
Not at all. They saw numbers as, like, divine principles, building blocks of the universe, not just tools for calculation.
And we have some really concrete, almost startling examples of this, right? Where language and math were combined to create things with, well, real-world power.
Absolutely. The starting point here is often gematria. That's the technique, basically, of assigning numerical values to words or names or whole phrases, and then taking that resulting number seriously, interpreting it.
Okay.
And when you do that specifically with a person's name, applying gematria to a name, that specific practice is called onomancy, name magic, essentially.
Onomancy. Right, and you mentioned city walls earlier. There's an actual example involving a king in construction from way back.
Yes, it's a really powerful anecdote. King Sargon II of Assyria, we're talking the 8th century BC here. Sources describe this Assyrian inscription where the king literally commissioned the wall of the city, Khorsabad, to be built exactly 16,283 cubits long.
16,283. That's incredibly specific. Why that number?
Because, according to the inscription, that precise length corresponded to the numerical value of his own name.
Wait, hold on. So this isn't just like writing something symbolic on a scroll somewhere. He actually changed a massive physical structure, a practical piece of engineering, a city wall, just to match a number derived from his name.
That's what the record suggests. It really shows how deeply ingrained this belief was. For someone like Sargon, this wasn't symbolism. It seems to have been considered part of the fundamental order of things. This was reality.
Wow. That really puts the power of the idea back then into perspective.
Definitely. And this kind of thinking wasn't just stuck in the Near East. It spread. By the 6th century BCE, you have the Greek tradition, particularly Pythagoras and his followers. They were practicing something called isopsephy. Think of it as the Greek version, or maybe the predecessor, of the Hebrew gematria we just talked about.
Pythagoras. Okay, so everyone knows his theorem, but he was also deep into this mystical number stuff.
Oh, absolutely. The Pythagorean tradition saw numbers as the key to understanding the cosmos, musically, mathematically, spiritually. Isopsephy was part of that.
And the Greeks, they seem to have really formalized this whole letter number thing, didn't they? How did they take it from this kind of philosophical practice and make it almost official?
Yeah, they codified it. They developed what's known as the Milesian system, named after the city of Miletus. In this system, each letter of the Greek alphabet was assigned a distinct numerical value. It was quite elegant, really.
So alpha is 1, beta is 2, and so on.
Pretty much, yeah, although it gets a bit more complex as you go up.
Right.
But the key thing is it was a standardized system. And because it was efficient, it spread like wildfire during the Hellenistic period, after Alexander the Great's conquests.
Right, so Greek culture was dominant then.
Exactly. And it became so accepted, so ingrained, that by the 3rd century BCE, in Hellenistic Egypt under Ptolemy II Philadelphus, This system, this, let's be honest, mystical mathematical tool, was officially adopted and integrated into state administration.
Integrated into the state. So they were using it for, what, record keeping taxes?
All of the above. But potentially also for statecraft. Maybe even interpreting omens. It blurred the lines. It was a tool for commerce, for governance, and potentially for prophecy, all rolled into one system.
Okay, that's fascinating. Let's jump forward a bit then. This core idea, letters have number values, it clearly becomes a kind of template, right? Lots of cultures adapt it.
That's exactly what happens. You see these alphanumeric systems popping up all over. You've got the Abjad numerals in Arabic, Hebrew numerals, Armenian numerals, alongside the Greek ones we just mentioned. Each culture develops its own way of linking its script to numbers. And presumably different methods for interpreting them, too.
Oh, definitely. And this leads to different, sometimes competing methodologies for actually doing the numerology or arithmancy. Some were kept simple, others became incredibly elaborate.
So what are the main ones we should know about? Well, the one that's probably most familiar to people today, especially in the West, is often called the Pythagorean method. Though its direct link back to Pythagoras himself is a bit debated, historically speaking. But the method itself is simple. You assign numbers 1 through 9 to the letters of the modern Latin alphabet, and you just repeat that cycle. A is 1, B is 2, I is 9, then J is 1, K is 2, and so on.
Right, so you'd take a name, assign the numbers, add them up, and keep reducing until you get a single digit, like a life path number or something.
Exactly. That's the basic idea behind a lot of popular numerology you might see online or in books today. Very straightforward.
But that wasn't the only game in town, historically.
Not by long shot. And not every system was focused just on names or divination in that direct sense. Some early attempts at what we might generously call science use numerology as a kind of foundational framework.
Like who?
Well, consider the Arab alchemist Jabir ibn Hayyan. He lived around the turn of the 9th century, a hugely influential figure in early chemistry, and famously, he framed his really intricate chemical experiments within this elaborate numerological system. His whole way of organizing substances, reactions, properties is based on the numerical values derived from the Arabic names of the substances he was working with.
So he thought the number derived from the word gold actually told him something fundamental about the chemical nature of gold.
Essentially, yes. It's a very different worldview, right? The idea was that the name wasn't arbitrary. It was linked to the essence, and numbers revealed that essence. If the world was created with measure and number, then the name must hold a key.
It's hard to wrap your head around now, that fluidity between what we'd call science and mysticism.
Absolutely. They weren't seen as separate domains in the same way. Which brings us forward again to the European Renaissance. This is where things get really formalized for the Western esoteric tradition, particularly with one key figure, Heinrich Cornelius Agrippa.
Agrippa, right. Early 16th century. His work, 3 books of occult philosophy, is hugely important for this stuff.
Immensely. And Agrippa took arithmancy and applied it systematically to the classical Latin alphabet. But, and this is a crucial distinction, his method wasn't that simple 1 to 9 repeating cycle we just discussed.
Okay, so how did Agrippa's system work? What made it different?
He used a place value system, likely drawing heavily from Jewish Kabbalistic traditions, particularly gematria methods. So letters would map to numbers 1, 2, 3, up to 9, but then it jumped. The next set of letters mapped to 10, 20, 30, up to 90, and the final set mapped to 100, 200, 300, and so on.
Ah, okay. So unlike the simple system where, say, J might be 1 and S might also be 1 after reduction, in Agrippa's method, S would have a much higher base value because it comes later in the alphabet.
Precisely. It gives significantly more weight to letters appearing later. It makes the calculations more complex, and proponents would argue it allows for a much more nuanced interpretation because the raw numerical totals can become very large and distinct.
It reflects that Kabbalistic idea of layers of meaning, maybe, treating the alphabet itself as this ordered, complex mathematical sequence.
That seems to be the underlying philosophy, yes. And just as a little historical aside, if you look at Agrippa's original tables, they might seem a bit odd to us. That's because when he was writing in the early 1500s, letters like U, J, and W weren't consistently treated as distinct letters in the Latin alphabet yet. So his tables reflect that older structure.
Right, the alphabet itself was still evolving. That's a good reminder.
And this more complex Agrippan-style approach, influenced by Kabbalah, eventually gets adapted into English too. You start seeing attempts to create an English gematria or English Kabbalah. There are early hints, maybe, in poets like John Skelton back in 1523, but it gets more formalized later on. People like Willis F. Whitehead were publishing systems around 1899.
So this drive, this human impulse to find meaning by converting letters to numbers, it just keeps adapting to new languages, new alphabets, new contexts. It never really goes away.
It really doesn't. And that persistence brings us eventually right into the modern era and into probably the most widespread numerological phenomenon of the last few decades, the whole idea of angel numbers.
Ah, yes, the repeating digits. 111, 444, you see them everywhere online, on license plates.
Exactly. Those specific sequences gained massive popularity, particularly in New Age circles and the media associated with them. They were really defined and popularized around 2004 by authors Doreen Virtue and Lynette Brown. The core idea presented was that these repeating numbers were messages, signs from angels, or benevolent spiritual guides.
Okay, so that's the origin. Pretty recent, actually.
Very recent in the grand scheme of things.
Yeah.
But here's where the modern story takes a really quite shocking twist, especially concerning that specific trend. You'd naturally assume that the creators of such a globally recognized concept, something that brought numerology to a huge new audience, would, stand by it.
Right, you'd think they'd defend their work.
Well, no, not in this case. In a very public and relatively recent development, this was in a 2024 interview, Doreen Virtue, arguably the primary popularizer of angel numbers, she completely renounced the entire concept.
Renounced it. What did she say?
Her words were pretty unambiguous. Regarding angel numbers, the concept she helped create, she said, quote, "It's garbage. I regret it, and I'm sorry that I made them."
Wow, it's garbage. That's astonishing. The person most associated with popularizing angel numbers now completely disavows them.
That's correct. It's a major piece of context that often gets missed when people talk about angel numbers today. The originator herself has publicly rejected the idea she spread.
Yet, despite that pretty high-profile dismissal from the source, the idea itself seems to have incredible cultural stickiness, right? It still pops up, people still reference it, it still seems to influence people.
Oh, absolutely. It tapped into something, clearly. And you still see numerological ideas influencing decisions in surprisingly public spheres. For example, there was the case of Susan Ley, an Australian member of parliament. Reports suggest she credibly altered the spelling of her first name from Susan with ones to Susan with two based on advice from a numerologist.
Really? Why? What was the supposed benefit?
The belief, apparently, was that the numerological value of Susan would bring more excitement or energy into her life compared to Susan.
Okay. And then you have celebrity culture, which often seems drawn to these kinds of symbolic systems.
Definitely. Gwyneth Paltrow, for instance, publicly spoke about entering what numerologists refer to as a 9-year cycle. In that system, the number 9 signifies a period of transformation, completion, letting go, closure. So it's used almost like a personal cyclical calendar for anticipating or framing major life changes.
So, on one hand, you've got this massive cultural footprint. It stretches from ancient kings literally shaping cities based on their name number, all the way to modern politicians and celebrities using it for personal guidance. But on the other hand, you have the scientific and, let's say, mainstream intellectual communities, which generally view the whole thing with extreme skepticism, right?
That's putting it mildly, yes. Within scientific discourse, the term numerology itself is often used almost colloquially as a kind of insult, a term of dismissal.
How so?
Well, if someone proposes a new scientific theory, but it seems to rely too heavily on finding neat numerical patterns or coincidences in the data rather than on solid, reproducible experimental evidence or a robust theoretical foundation, critics might label it numerology. It's basically shorthand for saying, you're just seeing patterns you want to see. This isn't real science.
Okay, so it's used to draw a line.
Yeah.
Observation and proof on one side, pattern seeking on the other.
That's the general idea in that context. And this is where the story gets really interesting and maybe a bit blurry even. That sharp line is complicated by history. Because some of the absolute giants of 20th century physics, the people who revolutionized our understanding of the universe, were themselves deeply, profoundly intrigued by certain numerical coincidences they encountered in their work. Coincidences they couldn't easily explain or ignore.
You're talking about figures like Paul Dirac, Herman Weyl, Arthur Stanley Eddington, some of the biggest names in physics.
Exactly. Those guys. They wrestled with what are sometimes called the cosmic constants, or the large number coincidences.
What kind of coincidences are we talking about?
Well, things like looking at the ratio between the electromagnetic force and gravity one is vastly stronger, but the ratio is this enormous specific number. Or comparing the age of the universe to the time it takes light to cross an atom again, you get these huge, seemingly arbitrary numbers that relate to each other in ways that just felt too neat, too structured to be purely random chance.
So these top-tier scientists were looking at the fundamental constants of nature and thinking, hang on, is there some hidden meaning or structure in these numbers, even if they didn't have a theory for why?
Precisely. They were fascinated, even disturbed sometimes, by these apparent patterns emerging from the fundamental laws of physics.
Why?
They didn't necessarily leap to mystical conclusions, but they acknowledged the profound oddness of it.
And probably the most famous example of this kind of, let's call it scientific number fascination, has to be Wolfgang Pauli, right? The quantum pioneer. He got fixated on one specific number.
Ah, yes. Pauli and the number 137.
Why 137? What was so special about it?
Well, 137, or technically it's reciprocal, roughly 1137, is the approximate value of the fine structure constant. This is a really fundamental dimensionless constant in physics. It characterizes the strength of the electromagnetic interaction. It pops up everywhere in quantum mechanics and electromagnetism. And Pauli became utterly captivated by this number. It's a prime number, which adds to the mystique. He spent a significant portion of his intellectual energy wondering why it had this specific value. He deeply suspected it held some kind of profound hidden significance, perhaps linking physics to deeper philosophical or even archetypal principles.
So, if scientists of Pauli's caliber are getting that obsessed with the meaning of a number that emerges from physics, it really does blur that line we talked about between dismissing all pattern seeking as numerology and acknowledging that sometimes numerical patterns are hinting at something deeper.
Exactly. That inherent tension, that gray area, was articulated brilliantly by a British mathematician named I.J. Good. He was also involved in code breaking at Bletchley Park. Really sharp mind. And Good put forward this very provocative argument that directly challenged the knee-jerk scientific dismissal of pattern seeking, of what looks like numerology. What did he argue? He argued that what we dismissively call numerology was actually, in many important historical cases, the origin point for major accepted scientific theories.
Wow, okay. He's saying the pattern came first before the scientific explanation, that the numerology led to the science.
That's the core of his claim. He pointed to specific examples. Things like Kirchhoff's laws in electrical circuits, Balmer's formula that predicted the spectral lines of hydrogen, Kepler's third law describing planetary motion, even key concepts in electromagnetism and foundational ideas in quantum mechanics. Good asserted that many of these monumental breakthroughs began their lives as essentially numerological formulae. That is, someone observed a striking mathematical pattern or relationship in the data before there was a comprehensive physical theory to explain why that pattern should exist.
So Kepler notices planets' orbital periods relate to their distances in this neat mathematical way, even before Newton comes along with the theory of gravity to explain it. That initial observation is, in Good's view, a form of successful numerology.
That's the kind of thing he was pointing to, yes. The pattern was recognized as significant, as likely true, even without the underlying why.
That's a really powerful counterpoint. But how did Good suggest we tell the difference between, just random patterns and these potentially meaningful numerological formula that might hint at real science?
He offered a really interesting definition. He argued that a correct or successful numerological formula is one that possesses what he called a good explanation.
A good explanation? What did he mean by that?
He meant that the explanation, the underlying theory that makes sense of the numerical pattern, might not be known to us yet. But crucially, he believed it exists somewhere in the vast universe of possible, logical, coherent ideas. So the formula is correct because it's tapping into a real underlying structure or law of the universe, even if we haven't formulated that law in the language of physics or science yet. The pattern itself is the clue that such a law exists to be found.
That's a fascinating way to think about it. The pattern points towards a theory that's waiting to be discovered.
Exactly. It reframes numerology not just as superstition, but potentially as the very first intuitive step towards uncovering deeper truths about reality.
So, thinking back over our whole journey today, we've gone from King Sargon II literally shaping his city wall 16,283 cubits to match his name,
through Agrippa's complex Renaissance tables, linking Latin letters to layered numerical values.
to the very modern rise and the surprising public rejection by its creator of angel numbers.
And finally, right into the heart of 20th and 21st century physics, where you have Nobel laureates wrestling with cosmic numerical coincidences and mathematicians like I.J. Good arguing that maybe just maybe, some numerology is actually proto-science.
It's quite a ride. So the key takeaway here, especially for you listening, the learner, seems to be about this enduring human quest. A quest for meaning, for order, whether we express it through mystical systems or through the rigorous language of science.
Precisely. Numbers seem to be the fundamental language we use to describe that order, or perhaps to impose order where we crave it. And across millennia, we just seem persistently compelled to read deep significance into numerical patterns.
Which leaves us with a final, pretty provocative thought to chew on. If I.J. Good has a point, if some of the world's most revolutionary scientific theories really did start out as observations of numerological formula, then what numerical patterns might exist today? Maybe it's an odd coincidence someone noticed in climate data, or a strange ratio popping up in economic models, or something unexpected in genetics. Patterns that hard science currently dismisses as just noise, just randomness.
Could one of those dismissed patterns actually hold the key? Could it be the first glimpse of a groundbreaking new theory, a whole new understanding of some aspect of reality that we just haven't figured out yet?
Is that search for meaning in numbers always just a quirk of our pattern-seeking brains? Or is it sometimes, maybe more often than we think, an intuitive first step towards uncovering the hidden physics, the hidden rules of the universe?
Something to ponder. Until next time, keep seeking the patterns.
Welcome to the Deep Dive. Today, we're getting into one of nature's, well, ultimate performance machines, the falcons, the genus Falco.
That's right. Incredible birds.
Yeah, and we're not just here to say, oh, they fly fast. We want to dig into the really surprising stuff, how they hunt, their anatomy.
Especially their family tree. That's
Right.
where things get really unexpected.
Exactly.
Yeah.
So our mission here is to sift through the biology, the history, all the sources we've looked at, and basically pull out the most compelling, maybe non-obvious facts for you. By the end of this, you should have a really clear picture of why these birds are just different.
Mm-hmm. And that difference is key. We are focusing strictly on the genus Falco. That's about, what, 40 species?
Around 40.
And they're incredibly successful. You find them pretty much everywhere, right? Every continent except Antarctica.
Though not currently in Antarctica.
Right, not today. But it's interesting, other closely related raptors did live there way, way back. We're talking tens of millions of years ago in the Eocene.
Wow, okay. But let's start with the headline feature, the thing everyone associates with falcons.
Speed.
Absolutely.
The numbers are just staggering, aren't they?
Yeah.
What are we actually talking about?
We're talking about the world record holder. Full stop. The peregrine falcon is the fastest animal on Earth, period.
In a dive, specifically.
In a dive, yes. Or stoop, as it's called in falconry terms. They're regularly clocked diving at 320 kilometers per hour.
Which is about 200 miles per hour.
Exactly. But the fastest ever recorded vertical dive, that hit 390 kilometers per hour.
240 miles per hour,
Yeah.
straight down. That's just hard to even imagine.
It really is. It requires an incredibly specialized body.
So how does their wing structure make that possible? It must be perfectly designed.
Oh, absolutely. The adult falcons, they have these very distinct wings, thin, quite tapered,
Sleek.
very sleek, and that shape is crucial. It lets them cut through the air with minimal drag, but also allows for those really rapid changes in direction you need when you're chasing something fast.
Makes sense. But what's maybe even more interesting is what the young birds have.
Oh, how are they different?
Well, fledglings birds, in their first year, they actually have longer flight feathers. Broader, too.
So less specialized.
Kind of, yeah. It gives them a wing shape that's more like a general-purpose bird. It makes flying easier, more stable, while they're still learning the ropes,
Yeah.
mastering those incredibly difficult aerial hunting skills.
Ah, okay. So they effectively get a set of learner wings before they graduate to the high-speed adult version.
That's a great way to put it. It's a really elegant biological trade-off.
So they've got the speed, the aerodynamics, but how do they actually kill their prey? And how is that different from, say, a big eagle?
Right. This is probably the defining feature of the whole Falco genus. It sets them apart. Falcons kill prey with their beaks.
With their beaks, not their talons. I always picture eagles grabbing things with those huge feet.
Exactly. That's the key difference. Hawks, eagles, kites, all those birds in the other big raptor family, the Accipitridae, They primarily use the crushing power of their talons.
Right.
Falcons, though, use a special feature on their beak. It's called the tomial tooth.
A tooth on a beak.
Well, it's not a real tooth like ours, obviously. It's a sharp notch, a projection on the side of the upper beak. And they use this tooth to quickly sever the spinal cord of their prey, usually at the neck.
Wow. Like a precise surgical strike.
Pretty much. It's incredibly efficient, especially for prey caught midair after one of those high-speed stoops. A quick, clean kill.
A tool perfectly suited to their hunting style. And to make that strike at 240 miles per hour, the vision must be extraordinary.
Oh, it's phenomenal. There was one study, they measured the visual acuity in one falcon species. It was 2.6 times better than a human's.
2.6 times.
Yeah. If you're moving that fast, you absolutely need the visual processing power to match incredible detail, depth perception tracking.
Okay, so I've got the physics, the weapon, the targeting system. Let's switch gears a bit and talk about the name. Falco. Linnaeus gave it that name in 1758. Where does falco come from?
It's late Latin. Comes from the word falx or faltis.
And that means?
A sickle, like the farming tool.
A sickle. Why a sickle?
Well, interestingly, it seems to refer specifically to the shape of the bird's claws, that curved shape. Not the beak or the speed, but the talons.
Huh. That's not what I would have guessed. And that Latin root gives us some other interesting terms, especially from falconry, right? Like tercel, the male falcon.
Ah, yes, tercel or sometimes tiercel. There are a couple of ideas about its origin.
Okay.
One older idea, which isn't really accepted much now, connects it to the Latin tertius, meaning third. Based on this old, mistaken belief that only 1 out of every 3 eggs hatched a male.
Oh, that sounds like folklore.
Pretty much, yeah. The much more accepted explanation is simpler. The male falcon is typically about 1/3 smaller than the female.
1/3 smaller. So the name literally comes from the size difference.
Seems like it, yes.
Yeah.
It reflects that reversed sexual dimorphism you see in many birds of prey, but it's quite pronounced in falcons.
And that size difference is important ecologically, isn't it?
Hugely important. Because the female is larger, she can often take larger prey than the male. So a breeding pair isn't competing directly for the exact same food sources. It broadens their collective menu, so to speak.
That makes sense. And speaking of size, the variation across the genus Falco is just massive.
Oh, enormous. You go from the absolute giant of the group, the gerfalcon found way up in the Arctic.
How big are they?
They can be up to 65 centimeters long. A really imposing bird.
Okay, huge.
And then at the other end of the scale, you have the pygmy falcon in Africa. Tiny little thing, barely 20 centimeters long.
Wow, from 65 down to 20 centimeters. But they all share that same basic body plan, the tapered wings, the tomial tooth.
That's the unifying factor, yes.
Yeah.
Despite the incredible size range, they all have that core falco toolkit.
It's kind of amazing. Okay, let's make a big shift now from how they look and hunt to where they came from, their evolutionary story. For a long time, everyone just lumped falcons in with hawks and eagles, right? Just birds of prey.
That was the traditional view, based purely on apparent inference, the hooked beak, the talons, the predatory lifestyle.
But modern genetics threw a massive curveball into that neat picture.
A huge one. Completely rewrote the family tree. Now, we do have very old fossils that are definitely falconids, part of the broader falcon family. Some go back as far as 55 million years ago.
Okay, so the lineage is ancient.
The lineage is ancient, but the real shocker came from sequencing their DNA, comparing their genes to other birds.
All right, lay it on us. If they aren't close relatives of hawks and eagles, what are they related to?
Okay, brace yourself. Despite looking and acting like the quintessential raptor, molecular studies show very clearly that falcons are not closely related to those other birds of prey in Accipiter.
Okay. So who are their cousins?
Their closest living relatives are parrots and songbirds.
Get out! Parrots and songbirds, like sparrows and budgies.
Exactly. Parrots and passerines. That's their closest family.
That must have turned ornithology upside down.
Oh, it caused quite a stir.
Yeah.
It means that the whole raptor body plan, the sharp beak, the talons, the hunting adaptations, evolved completely independently in falcons.
So it's convergent evolution. They ended up looking like hawks because they do a similar job, but they came from a totally different starting point.
Precisely. It's one of the most stunning examples of convergent evolution in the bird world. They arrived at the raptor solution from a completely different branch of the avian tree. Incredible.
Okay. And where did this lineage likely start geographically?
Well, based on where we find the fossils and the distribution of living species, the best guess points towards an origin in either North America, Africa, or maybe the Middle East or Europe. It's still debated, but they clearly spread out globally from somewhere in the Northern Hemisphere or Africa.
They definitely got around. So with 40 species spread across the globe doing slightly different things, how do scientists make sense of them all? Are there subgroups within Falco?
Yeah, there are. To make it manageable, biologists usually talk about 4 informal groups. It's not super strict taxonomy, but it's based on their general size, appearance, and, importantly, their hunting style. It's a really helpful way to think about them.
Okay, let's break those down. What's the first group?
First up, you've got the kestrels. These are typically the smaller, often stockier falcons. Think brown plumage on the back, often quite patterned.
And they're known for?
Hovering. That's their signature move. You'll see them hanging stationary in the air over fields or roadsides, scanning the ground below.
What are they looking for?
Mostly things on the ground. Small mammals like voles, lizards, big insects. They're ground hunters, primarily. And you could even split them further. Some kestrels have that classic dark Miller stripe under the eye, like the common kestrel, while others, like the lesser kestrel, don't really have it.
Okay, so kestrels, small, brown, hoverers, ground prey. Got it. Group number 2.
Second group, the hobbies. These guys are generally a bit larger than kestrels. They tend to have a lot of dark slate gray in their plumage.
And Mallard stripe.
Almost always present and usually very bold, gives them a sort of masked look.
And their hunting style, are they hoverers too?
No, hobbies are built for speed and agility in the air. They are primarily hunters of other birds, often catching swallows, martins, or even dragonflies on the wing. They're incredibly fast and acrobatic flyers, often hunting at dawn and dusk.
Aerial acrobats. Okay. Group 3 must be the big guns, right?
Third group, the peregrine group. This is where you find the peregrine falcon itself, the speed champ. These are powerful falcons. The sizes vary quite a bit within the group. They usually have that black Muller stripe and often a distinct black cap or hood.
And their patterning.
Typically, quite finely patterned underneath, often with clear horizontal bars across the belly and chest. Very crisp looking.
And they hunt.
They're versatile. They take medium-sized birds in spectacular high-speed stoops, but also mammals and other terrestrial vertebrates. They're the classic, powerful, all-round falcon.
Right, and the last group, you mentioned 4.
The fourth group, the hierofalcons, sometimes called the hawk falcons.
Hawk falcons, why?
Because honestly, they look a bit more like hawks than the other groups do. They often have more reddish-brown or gray-brown colors, and their patterns can be more complex, more streaky, or mottled.
Okay, so less of the clean slate gray and barring.
Exactly. And a key difference. Look at their undersides. Instead of horizontal bars like the peregrine group, hierofalcons tend to have patterns running lengthwise, streaks, blotches, arrowhead shapes.
Ah, okay, that's a good visual clue.
Yeah. Think gerfalcon, saker falcon, lanner falcon. Those are hierofalcons. And what's really interesting is that this group is evolutionarily quite young. They only seem to have emerged in the last couple of million years.
Only 2 million. That's super recent in evolutionary terms.
It really is. A relatively new branch of the falco tree.
Okay, so those 4 groups, kestrels, hobbies, peregrines, and hierofalcons, help sort out the diversity. Let's just throw out a few specific names to reinforce this. We've mentioned the peregrine, Falco peregrinus, found basically everywhere.
The ultimate cosmopolitan.
And in North America, the bird many people call the sparrowhawk is actually
The American kestrel, Falco sparvarius. A true kestrel, despite the common name.
right. And the biggest one again? The Arctic specialist.
That's the gerfalcon, Falco rusticulus, the king of the hierofalcons, found across Greenland, Arctic Canada, Iceland, northern Scandinavia, and Russia.
And sadly, some species haven't made it.
No. Like the Reunion kestrel, Falco du Bois, it went extinct around 1700, likely due to human activity after the island was settled, a reminder of their vulnerability.
Definitely. Now, going back even further into the fossil record, you mentioned it can be tricky identifying ancient falcons. Taxonomy isn't always straightforward.
Not at all. The fossil record for birds is often fragmentary, small, delicate bones don't preserve well. And sometimes initial interpretations are just wrong.
What? Any examples?
Well, there was a fossil found in Italy, initially named Falco pissanus. Everyone thought, okay, an ancient falcon.
Makes sense.
But later analysis, looking more closely at the bone structure, turned out it wasn't a falcon at all.
What was it?
It was a pigeon from the genus Columba.
A pigeon. Wow, that's quite a mix-up. From a predator to, well, prey.
Exactly. It highlights how careful scientists have to be. And speaking of scientific correction, you mentioned the hierofalcons in DNA earlier. There was a bit of a story there, wasn't there, about their placement on the family tree.
Ah, yes, the NUMT issue. Okay, so initially, some genetic studies seem to show that the hierofalcons were basal.
Meaning they were really old, like representing the earliest branch of the living falcon.
Exactly, that they split off first from the ancestor of all modern falco. That was the interpretation of some early mitochondrial DNA data.
Okay.
But then scientists discovered something called NUMT, that stands for nuclear mitochondrial DNA sequence.
The nuclear mitochondrial, that sounds contradictory.
It does. Basically, mitochondrial DNA, mtDNA, is what we usually use for tracking recent evolution because it's separate from the main nuclear DNA and mutates relatively quickly.
Right, inherited from the mother.
Yes. But sometimes, purely by chance, a chunk of that mtDNA gets copied and accidentally inserted into the DNA in the cell's nucleus, an NUMT.
Okay, a misplaced copy.
Exactly. And these NMNTs are often degraded or evolve differently once they're in the nucleus. If researchers accidentally sequence this fossil NUMT sequence from the nuclear DNA, thinking it's the real functional mtDNA from the mitochondria,
It messes up the results.
big time. It can make lineages look much older or younger than they really are.
Yeah.
And that's what happened with hierofalcons.
So they found NUMT.
They found the specific NUMT that had skewed the initial results. Once they identified it and analyzed the actual mitochondrial DNA properly, it completely changed the picture.
And confirmed.
That the hierofalcons are not basal at all. They are indeed a very recent group, confirming that 2-million-year origin we talked about earlier. That's fascinating. A tiny bit of misplaced DNA rewriting evolutionary history. It really shows how science corrects itself.
Absolutely. It's a process.
Okay, let's try and pull all these threads together then. We've covered the incredible speed, that unique hunting tool, the toemeal tooth.
And the absolute bombshell that their closest relatives are parrots and songbirds, not other raptors.
Right. And the 4 main groups: kestrels, hobbies, peregrines, and the recent hierofalcons.
When you look at the timeline, what really stands out is how fast much of this diversification happened. Those main groups, the kestrels, hobbies, peregrines, they really radiated, split into different forms between about 5.3 and 2.4 million years ago.
Okay, and what was happening in the world back then?
That period, the transition from the Miocene to the Pliocene epoch, was a time of major global environmental change. Crucially, it saw a huge expansion of open habitats, grasslands, savannas spreading across the continents.
Ah, so the world opened up.
Exactly. And it seemed like that opening up of the landscape provided the perfect opportunity, the perfect ecological stage for falcons to diversify rapidly. New niches opened up, favoring different hunting styles.
So the rise of grasslands literally fueled the evolution of these different falcon types. They didn't just adapt, they exploded onto the scene.
It really looks that way. The changing environment seems to have been a major driver for their relatively rapid specialization.
It's incredible. So a final thought for everyone listening.
Well, I think next time you see a bird of prey soaring overhead, whether it's hanging still like a kestrel or rocketing past like a peregrine, just remember you're looking at this ancient lineage, yes, but one that's also a product of surprisingly recent rapid evolution. And they're still adapting.
And maybe try to figure out which group it belongs to.
Definitely. Think about how it's behaving, what it looks like. Is it a hoverer, a high-speed hunter, maybe one of the hawk falcons? See if you can spot the dominant group in your local area. It's a great way to start your own deep dive into these amazing birds.